a SNARK is a zero-knowledge proof, and they're very good at taking information from the real world, putting it in the blockchain. But the process of producing these SNARKs can be very expensive. Hence, the idea of using a SNARK ASIC to accelerate that. Okay, so just to make sure we're on the same page, an ASIC stands for Application-Specific Integrated Circuit. And as the name suggests, it's a circuit, so a piece of hardware generally implemented, in silicon, and it's application-specific. Meaning that it's, instead of being general purpose like a CPU or programmable like a GPU even, it has a more focused reason to be. And because of this focus, you get a huge amount of performance. So we've already had 50 years of Moore's law, and what ASICs provide are basically orders of magnitude beyond Moore's law. So you can think of 10, 100, 1,000x, or even possibly up to 1,000,000x performance improvements for a very specific algorithm that you might be running. But what are the costs of ASICs? So you don't want to start an ASIC project lightly, because they're quite expensive. Like financially, they're expensive. They would cost on the order of $10 million. You can do it for less, for more, but that's the rough order of magnitude. And they also take a lot of time. If you were to start from scratch, you'd expect 1 to maybe even 3 years to complete an ASIC from the very beginning to when it's shipped to people. And so you kind of want to have this VC mindset where you're very selective and you make these relatively large upfront investments in order to reap the rewards over the long term, multiple times your investment. Okay, so just to give you orders of magnitude, an idea as to how much ASICs can help for specific algorithms, we have the Bitcoin proof of work from which we can learn from. The algorithm is double SHA-256, and the specific metric that's of interest here is power consumption per unit of work, so per double SHA-256. And it turns out that the performance gains compared to CPU is 250,000 times. Which is an enormous number. Usually you don't get such a dramatic improvement, but that's what has happened over 10 years, thanks to because of this massive industry around proof of work. And one interesting tidbit here is that the mining industry is so big that it has reached cryptographic scale. And by cryptographic scale, I mean that usually you'll set a security parameter in your cryptographic systems, and you might set it to 80 bits or 90 bits or whatever, 128 bits. And Bitcoin mining is over 80 bits. So there's a block hash with over 80 bits of leading zeros. There's over 2,000 of such block hashes. And this is the record with 91 0 bits, which is very impressive. Okay. The other example that we have in terms of ASICs in the blockchain space is in the context of VDFs, verifiable delay functions. And the idea here is to try and use sequential computation to mimic kind of the notion of physical time. And so here your metric is going to be latency. And the improvement that we're seeing here is 1,000x compared to CPUs. So again, a huge improvement. And so the question we can ask ourselves is, what if we try and take these huge performance gains and apply them to the world of SNARK proving? And I believe we would be removing one of the big bottlenecks of SNARKs, which is just the proving time. It just takes too long to build these proofs. Okay, so I just want to present a quick mental framework for thinking of ASICs, and kind of maybe it's maybe not intuitive, but it's kind of the oracle problem. So you have the real world, and then you have a computer, which could be a blockchain computer or a real computer. And the computer needs to be aware of the real world. Kind of when it's born, the computer is dumb. It has no notion of what the real world is. And so you need to bring in the information. And so what you would do with traditional computers is you use sensors. But in the blockchain space, we don't have the luxury of using sensors, because the sensory world is kind of it's subjective, and it's difficult to convince others that you're sensing a specific thing. And so really the tool that you need is digital stuff, something that's trustless. And really the ultimate mechanism here is cryptography. And so in the same way that we have, oracles, sound oracles, video oracles, touch oracles for traditional computer, we need to find equivalent or like some sort of oracle for the blockchain world that gives meaning to the blockchain. And the first oracle that gave meaning to blockchains was the energy oracle. So proof of work basically is a way to connect blockchains which are dumb to the notion of energy expenditure. That's what it is. And VDFs basically do the exact same thing, but with time. So VDFs are a time oracle. They give meaning to blockchains by taking information in the physical world and bring it in. And I mean, one thing to notice here is that the blockchain is like a very weak computationally. One blockchain would be like roughly the equivalent of a mobile phone in terms of computational power. Even with sharding, you have 1,000 mobile phones that's shared across the whole world. So really, these what you include in the blockchain needs to be very succinct proofs. And that was easy to do with energy, but it took a bit of time to come up with VDFs. And the V stands for verifiable, which means that you have these fast to verify proofs. Anyway, so these two things are actually very similar. Like the two sides of the same coin. One is massively parallel computation, and the other one is just inherently sequential computation. And then kind of the third oracle, which I think fits in this framework, is kind of the proof oracle. So you have statements around the real world that you can like phrase cryptographically with like secrets and statements and stuff like that. And what you want to do is put the statements on the blockchain, but also the proof. And in some cases, the proof can be very big in terms of data or very expensive to compute. And so you have this general purpose mechanism, SNARKs, to basically compress the data, compress the verification time so that this proof oracle can just give you the proof and it's appropriate for the world of blockchain. So it's an appropriate mechanism for incorporating cryptographic ideas and statements onto the blockchain. And again, the blockchain is computationally very restricted, and so in the outside world off-chain, this is where you have lots of computational power, and you want to try and leverage it. And one way to leverage it is using ASICs. And the reason why we have ASICs for the first two is security. So if you have someone who, for example, has a mining ASIC which is 100 times more power efficient than the rest of the network, well, they just need to spend 0.5% of the total energy consumption. They'd be able to conduct a 51% attack. So it's kind of important that everyone is kind of pushing towards the race to zero at roughly the same speed, so that there aren't these like massive advantages between people. Okay, and there's also SNARKs kind of go beyond kind of towards blockchains. They kind of go outside blockchains. So you can take information about blockchains and give them to other devices that are restricted, such as light clients. So that's also helpful. And there's various projects that are doing that. So there's Cello and Coda that are basically using zero-knowledge proofs for light clients to compress, for example, header chains and things like that. And you could also do it in the context of Plasma. So PG is the Plasma group, where basically you compress. Plasma has all these very long, Merkle proofs, and so you can compress them and then give the compressed Merkle proof to the light client. And then the cool thing is that SNARKs are also really useful in the context of inter-blockchain communication and interoperability. And the reason is that you can have two-way light clients with SNARKs passing between both blockchains. So that's basically like a sidechain model. Okay, and then there's various projects that are investigating this interoperability idea. And then another aspect of it is that SNARKs are very appropriate in the service model, where the user doesn't necessarily kind of want to have an ASIC or want to have lots of computational power. They have their phone, and so this model of outsourcing it works pretty well, so long as it's off-chain, outside of the blockchain. The one downside of this model is that even though you're not trusting the service for safety, you are trusting the service for liveness. So if the service provider goes down, then you need to kind of find another service, or you need to have you need to have backup mechanisms. And like Zcash, I believe allows that, so that you can, without compromising privacy, you can craft a transaction, do a little bit of work on your phone, and then give that to a service provider who will do the full-fledged SNARK proving, and then that SNARK proof can then go onto the Zcash blockchain. And they have other providers that are looking into this business model, like Starkware. And before I go into the next section of my talk, I just want to say that in addition to the direct benefits of working with hardware, there's kind of these indirect synergies. And one which is especially relevant to SNARKs is that SNARKs, at the end of the day, a lot of it is about circuits. And hardware, at the end of the day, is also about circuits. And it's just that they're slightly different circuits. In hardware, you have Boolean circuits, whereas in SNARKs, you have these arithmetic circuits. But a lot of the tools and techniques I believe, can be basically ported over from the hardware world into the blockchain world. So things like formal verification. Hardware people have been doing formal verification for decades. And the reason they've been doing it for decades is because if there's a bug in your ASIC, you spent millions of dollars and you have to trash your ASIC. So it's a little bit like industries like the aerospace, where these things are so expensive that you want to make sure they're bug-free from the get-go. And so they have lots of experience. They also have experience with compilation and optimization of circuits. And for example, optimizing the circuit complexity of SNARKs is important because that improves, for example, the proving time, which can be a bottleneck. Okay, so that's kind of the high-level picture of blockchain ASICs, and more specifically SNARK prover ASICs. And now I kind of want to give a little bit of flavor about how you would actually go about building such a thing, the execution. And hardware is all about the execution. So one thing I'd suggest to whoever would try this is to basically outsource to professionals. But at the same time, you kind of want to have people who are somewhat familiar with the blockchain space as well, so that you speak the same language. So outsource, because within the blockchain space, we are not experts. Other than this small class of companies, which is the mining ASIC companies. So when we announced the VDF project, we had maybe 10, almost all the mining companies came to us, and we talked to them, and they understood our language. So these are potential people you can outsource to. But the mining companies generally will produce a product. So in addition to the product companies, you also have consultancies that have spun up. So there's 3 of them here: Obelisk, Supranational, Epic. And the one that we're working with for the VDF project is Supranational. And Supranational was actually was founded specifically to work on the VDF project. And I think it's quite an inspiring story because it was founded by 3 Intel people who 2 of which were there for 20 years. And they basically decided to leave Intel to work specifically in the blockchain space and to start with the VDF project. Okay, so if we are going to build a SNARK ASIC, we need to make decisions as to which SNARK ASIC we're going to build. And you want to, because you only have one shot, you can't, you don't have that many shots. So you need to choose a construction. And I personally believe that the future of SNARKs is universal SNARKs. And universal SNARKs means that the SNARK proof scheme works for every single circuit, without having to do a trusted setup for every individual circuit. It's just too expensive from a coordination perspective and from a trust perspective to have to do all these ceremonies all the time. So for a long time, since 2017, STARKs was like the only universal SNARK out there. But then, in in 2019, we saw this explosion of ideas. It started with Sonic earlier this year, and then we had Planck, which was maybe a couple weeks ago, something like that. And then just 2 or 3 days ago, we've had these new ideas where you can use RSA groups and class groups, and there's this Halo idea. So a lot of stuff is going on, and this is very exciting. And I guess we need the dust to settle a little bit before we pick a winner. But I think the winner is going to be in this group or something very close. And so, on the flip side, the non-universal proof schemes, such as, for example, Graph 16, I think will have a hard time being the ultimate winners, precisely because they're not universal, and as such, they're not hard. Maybe, I don't know, maybe not hardware friendly. Well, so within these schemes, they're all interesting, but one kind of in the context of hardware stands out, and that's the one which is based on RSA groups. And the reason is that the VDF work that we're doing with the VDF Alliance is actually an RSA VDF. So the basic operation is the same. You work in an RSA group, and the operation is a modular squaring. And so we've already put a lot of investment in making sure that these operations are very, very fast. And so there's kind of a natural progression from an RSA VDF ASIC to a SNARK, RSA SNARK ASIC. So that's one thing we should consider. And to give concrete numbers, the ASIC that we're building will have a latency of 1 nanosecond per operation. And so one of the things you can do with SNARKs, which is amazing, is that you can massively parallelize. So you can imagine, for example, building an ASIC which itself has, let's say, 128 of these 1 nanosecond per operation cores. And then this is kind of back of the envelope calculations, but you can see that if you take, for example, 1 million gates, so that's 2 to the 20 gates in your circuit, your prover time using the technology that we're building right now would be very, very small, 20 milliseconds. And that beats the state of the art, by orders of magnitude. If you were to use, a CPU, a GPU, or even an FPGA, the second best thing is orders of magnitude worse than this. So yeah, quite exciting. But of course, we don't have to build an RSA SNARK ASIC. We can have a look at other constructions as well. The other thing I guess we want to do in the flavor of maximizing utility is, if we do go with a scheme which is based on elliptic curves, then we want to choose our curves properly. And here there's a few choices which makes it difficult in the world of hardware, because in hardware you kind of have to make a decision. You don't have the flexibility of software. And good candidates are, for example, the Zexi curves, where you can do one level of recursion. There's also the MNT curves, where you can do arbitrary recursion. And then, kind of in conflict almost with utility, there's the notion of standardization and de facto standards. So right now, BLS 12381 is being implemented by the blockchain industry almost as a blockchain standard. It doesn't have all this nice recursion, which is a shame. And then there's also, BN 254, which, is used in production in many systems today. So we're going to have to make a decision if we do go in this direction. And, we ultimately might be, quote, leaders in standardization. Whatever we build might actually become the de facto standard. So I guess with a lot of power also comes responsibility in making good decisions. Okay, so if you want to build an ASIC, you need to, I guess, outsource to professionals. You want to choose the right construction because you only have one shot. You also want to bootstrap your way up, and the traditional way that you bootstrap in hardware is you start at CPU and then you go to GPU, FPGA, ASICs. And this is the story that we've seen in proof of work. And in VDFs and basically everywhere. So, for Bitcoin proof of work, over the years we saw different solutions, and at each step you get a significant performance gain. like at least 10x at every step, which is amazing. And this is like for VDFs. So something very similar to VDFs is the notion of a time lock puzzle, and is the idea of encrypting to the future. Anyway, so there was this puzzle that was created by Ron Rivest, and it was solved by this guy using his CPU on his computer. And then the VDF Alliance, which was working on VDS but could apply its work also to time lock puzzle, used an FPGA. And this is the FPGA we use. And you had like a huge speed up here, from 1 microsecond per operation to 66 nanoseconds. And we believe that the ASIC that we're looking to build will do 1 nanosecond per operation. And so really we want to try and do the same thing for SNARKs. And the cool thing is that we're already seeing that organically happen. So there's the Matter Labs team who have been experimenting with GPUs, and they have one GPU which is 3.5 times faster than the 16-core CPU. So already here we're seeing significant gains, which is exciting. The Zcash Foundation has also been doing FPGA research work, and they specifically built this BLS12381 coprocessor, and I mean, actually, I was a little bit surprised by the results. Like, it seemed like the performance jump was not as high as I was expecting, but this is very early days, so maybe I guess we need more experimentation and to see what kind of performance we can get on FPGAs. And the FPGA step is kind of really critical because FPGAs and ASICs have lots of similarities. In particular, they're programmed the same way using the same kind of language, the hardware description language like Verilog or VHDL, and they kind of structured in a similar way. So the ASICs goes down to the transistor, and the FPGA is just like a small level of abstraction on top of transistors. But yeah, we still need some sort of team to go ahead and lead this SNARK ASIC effort, which I think would be very valuable. Okay, another thing that I would do in the execution is encourage competition. So Bitcoin was brilliantly designed as a massive worldwide competition, which led to billions of dollars in bounties, and we've seen the gains there. And a similar strategy has been taken in the world of VDF. So Chia, which is also doing a VDF, has had 2 competitions, each of size 100K, and they got a 4x speed up in the first competition, and then they got a 2x speed up on top of the 4x. So they spent $200,000, and they got an 8x speed up in the operation, which is based on class groups, which is amazing. And they're looking to do an FPGA competition soon, and we'll see what kind of speed up they get there. And the VDF Alliance is right now conducting an FPGA competition. So if you're in the hardware world and you want to compete for cash, then there's this 100K competition which is going right now. And if you know how to work with ASICs, we're actually looking to do a $1 million competition later next year. So basically, who can build like the fastest modular squaring in hardware? And one of the reasons why we can kind of justify having such a big bounty is that you can very easily spend lots of money with very advanced processes. So you can go down to 16 nanometer or 10 nanometer or 7 nanometers. It's kind of like the rough size of your transistors. And every time you go down, it's getting more and more expensive. And so it's economically it's much better to try and squeeze as much as you can in the abstract circuits than it is to invest in the fancy processes. So $1 million in the grand scheme of things in the wider project is actually not that much, but for competition it's massive. Like there's very few open competitions with a $1 million prize. Okay, and then in the world of SNARKs, we've already had a competition, and it's been very successful, I'd say. So Coda, that is using these recursive SNARKs, had a $100,000 GPU competition, and this is what the numbers they gave me, they got a 3.x speed up over the initial benchmark that they had, which is a huge optimization. And they got these 94 submissions, and also they're now working with the winner. So it's kind of also a recruiting opportunity. If you're in the hardware space and you want to come into the blockchain space, then participating in these competitions is a way to get noticed. And again, I'm hoping to see some sort of SNARK alliance, move forward these competitions and encourage innovation. On the topic of processes, like as I was saying, like every single process jump is now becoming more and more expensive. So the jump from, let's say, 16 nanometer to 10 nanometer might be 2 million. I don't know. I'm just $2 million, let's say. The jump from 10 to 7 might be $5 million, and the jump from 7 to 5 might be $10 million. Just to give you like an idea. And so while Bitcoin mining has to be kind of on the bleeding edge, because there's this constant competition and it's all about margins, the VDFs can afford to be less on the bleeding edge, and that gives us a bit of breathing space to financially. And it's possible that SNARKs can have even more breathing space. And the reason is that in VDFs you have this security constraint that if you're not fast enough, then basically the security of the systems that you build start to deteriorate. Whereas in SNARKs, it's kind of like a utility thing. It's like, is it good enough? Is it fast enough that it solves my specific problem in the real world? So because you don't have this kind of paranoia and then like a security thing in mind, maybe you can afford 28 nanometer. So you'll have less power efficiency, less performance, greater like die area, but it doesn't matter. And so you'll save a lot on the masks. So a lot of the costs of these ASICs is in the masks. So basically the stencils that are used to produce these ASICs where light shines through these masks. Okay, I mean, one of the things about the blockchain space is that it's very oriented towards the open source mentality. And even though we haven't seen open Bitcoin ASICs because it's very proprietary and there's lots of competition and it's all about money making, we're really trying very hard in the context of VDFs to be open. And so this is kind of the hardware stack, and we're trying to open as much as possible. All the way from the manual enclosure, firmware, PCB. RTL is going to be the code that specifies the circuits, and the net list is going to be the diagram with the gates and the wires and how they're connected. All of this will be open source. Unfortunately, like the foundry, which is like the place where these ASICs get built, they have a lot of IP that they want to keep secret. So there's this kind of this tension, but we're trying our best to open source as much as we can. And by doing so, you get lots of benefits. You get people who are kind of culturally, ideologically very aligned to what you do. I mentioned the Intel story. Part of the reason these engineers were happy to leave Intel is because they felt really compelled by the idea of open source hardware, and which is something which is very novel in the hardware space, which is kind of mostly dominated by NDAs and patents and whatnot. And in addition to these kind of 2 layers of the stack or 3 layers of the stack which are kind of protected, there's also components that we might want to use which it wouldn't make sense to reinvent them off the shelf. So we'd use a vendor, and the vendor would also have to keep them secret. Okay, and this is my final slide. So the final thing I'd suggest to any team that would execute such a project is to try and team up. And it's been quite a success story in the case of VDF. So we have 4 different blockchain projects that are funding this project. So it's for VDF specifically, it's a $15 million project, and thankfully we have all these foundations that are contributing, and this is fantastic. And there's a 4th one here that will be announced very soon. It was just confirmed a couple of days ago. So these are basically those who will ultimately use the ASIC and who are happy to fund it. And also because a lot of these foundations are also, part of their mission is to fund common goods. And this is kind of a perfect example of a common good. We also need to partner with academics and people who are specialized in the application. And so this is who we've partnered with at the VDF Alliance. And you also need to partner with hardware people. And so these three companies are partners in the FPGA competition that I mentioned. And these are like some of the biggest names in the hardware space. So yeah, it would be really nice to try and replicate this collaboration and this teaming up in the SNARK world. Whew, thank you.